be.
Which one are you guys doing yet?
Live audience from all over the world. How's that?
Is he just videoing it or is he doing a video?
No, it's video. Did you watch the whole thing last? You watched the whole thing? Oh wow.
Oh, was I supposed to?
No, you weren't. It was a long one.
I might have watched
Just
it.
an hour.
I'm not paying attention. Maybe he's doing Facebook Live.
I'm not sure how.
I hope not. Hello world. Hello Megan. Hope you're feeling better. I don't know if that's why you're gone, but okay. All right, let's score your homework. So we did not do section 14 or 15.4 last time. So we'll do those questions today. I'm not sure which ones they were. But let's see.
That's a little we're talking
Oh my
about.
goodness.
That takes a little while.
Those are books. I almost forgot.
It would have been fine.
I actually didn't understand.
I don't even know what it
Well,
is.
that'll show by this pop quiz.
What did I read? At least
What was that?
Julie.
We're doing a pop quiz to start off, so make sure you're doing it with us.
Can't look at your book.
Nope, no
If
books
she
allowed.
aces it, it's because she cheated. It's me.
No skipping forward and then coming back. Straight through. 1 through 5 as normal. All right. So question number 1 for this pop quiz is, what is the equilibrium constant for the ionization of water called?
What? The ionization.
Ionization of water. So water breaking up into hydronium ions.
Oh,
Remember this little thing?
no.
Oh my goodness.
Not really.
Yeah, I did. Because I did those and I figured them out. What?
What is this called?
Uh,
That's what they're asking.
I had just written that too.
That's what they're asking. What is the equilibrium constant for the ionization of water called? Remember, there's like different names for different equilibrium constants. Like, I forget what the others were that we learned a couple chapters ago. It was something constant, something constant. So what is this one called? And once you have that answered out, we'll go on to the next one. So number 2 is a solution with a pH of 9 neutral, acidic, or basic. So that one's a little bit easier than the first one. So is it
done that because I didn't read it.
a solution with a pH of 9, neutral, acidic, or basic? Number 3, the negative logarithm of hydronium ion concentration is the what?
Can you finish the question?
That is the question.
Don't say that
The
again.
negative logarithm of hydronium ion concentration is the
What's a law?
Did you not read it?
It did. She forgot.
No, the logarithms. I worked out those problems actually.
Oh, I
I
didn't.
mean, application 2. What problems?
so
Go on to the examples.
the negative logarithm of hydronium ion concentration is the When you
So-
figure the negative logarithm of the hydronium ion concentration, what is that?
Know that means.
It'll make sense. I promise. Hopefully.
So,
Yeah.
let's just go on this method.
Kind of going the first thing that comes to mind. I can guarantee you it's not right.
I think I actually think I read this.
It's not some mathematical equation or anything like that. Number 4, true or false? At 25 degrees Celsius, the sum of pH and pOH equals 14.
You really should know this one.
Yeah.
Okay. I don't know.
Just
The sum
Yes.
added together.
Yes. So when you add the pH and the pOH together, it equals 14
Oh.
at 25 degrees Celsius. All right. And number 5, what general term refers to organic acids and bases whose color changes with the pH of the solution?
I can't read this part.
I remember reading this.
What general term refers to organic acids and bases whose color changes with the pH of the solution? Do you need any repeat it?
Go, doesn't matter.
I wonder if we're.
Yeah, it's not gonna
You should have an answer for each one, even if it's the moon. Right, everyone have answers down. Awesome. Sweet. Okay, so number 1, what is the equilibrium constant for the ionization of water called? It is called the ion product constant of water.
Water equilibrium constant.
Just H2O constant.
Was that close to what you had?
No.
No, I wasn't expecting. The ion product constant of water.
H2O.
Ion product constant of water. That's the equilibrium constant for that.
I highlighted it.
Yep. Okay. Number 2, it is basic.
That was a pretty basic question.
And then number 3,
That was
it is the pH. So the negative logarithm of concentration of hydronium ions is the pH.
Duh.
So when you figure that out, it's the pH.
Sounds good.
You find it.
POH.
What was that?
Have the POH.
Oh, seriously?
Yeah.
And then
Talk about water.
4. Number 4 is true.
Do it. Buttergreen. I have the answer.
I think it was one of the questions. So.
Really?
Yeah. And number 5 is indicators. Or acid-base indicators.
We just have indicator.
What was that?
We just have indicator.
Well,
We just have
that's,
indicator.
yeah, indicators. Specifically acid-base indicators. That's what they are.
I got over by 50%.
I got a 40.
3 or 5?
Or, no.
It's more than 50.
Yeah,
66.
got plus 50.
Exactly. So, Megan, hopefully you did well on that one. Students watching, hopefully you aced that pop quiz. All right, now we can go to the homework.
Read this. I don't remember what you read.
Okay, so we were supposed to do.
No, I thought you'd read it. You remember what you read.
You do.
Oh.
This lesson I didn't.
I forget what all questions did we answer in the last class. Oh, we did those. Okay. So you didn't do any of the work on page 257. Because we're gonna do some of that in classwork. So we'll leave that for right now. But other than that, so 256 applications 1 and 2. So page 256 applications 1 and 2.
I'm really confused.
So number 1, write net ionic equations for each of the following
More
reactions.
confident about the first one.
Okay.
I looked at it and
Did you guys get down answers for these?
I tried.
The first
but-
one,
I tried. I just guessed.
I was not sure. I wasn't sure on the first one.
are you done?
Yeah.
Okay. I did application 1, like application 2, and didn't really do it.
I thought that was easier than the first.
I didn't know what to do.
I'm not good.
Alright.
I did it. I think I got it right. Yeah. Super hot.
Okay, so remember, ionic equations, purpose of ionic equations is to rewrite equations so that we only have the ions. So we can see which molecules dissociate into ions and which of those ions actually changed. So which one's actually donated a proton, which one's actually gained a proton, so that we don't just have this massive formula for equation that we started with that maybe has some useless information on it. So remember, so the first one's Na2CO3 plus CaCO2 CaCO3 plus NaCO. So, Ryan, do you have an answer for this one?
This is the only one I don't have it. I wrote it down as ions, but this is the only one I don't have a answer to, like the actual thing. I wrote it out like that, and I wasn't sure if that was right. But I didn't know which one to get rid of. That confused me.
Okay. So if we look at our table, because you remember, so to make an ionic equation, all soluble ionic compounds, all strong acids and strong bases, we write as separate ions. And then,
If they're soluble or not.
what was that?
How do you know if they're soluble?
If they're aqueous,
Oh.
then it means they're dissolved in water. And if they're not, then it means.
I should have done that before.
So,
I felt like I just guessed.
and then all insoluble substances, weak acids and weak bases, we keep them in their molecular forms. So, other than that, we will split them into ions. So, first one, which is Na2CO3, look on the table. Where's that? So go in here, there's CO3 too, which is a carbonate ion, which is a strong base. And if it's a strong base, then we will, and it's aqueous.
Yes. It's like mom.
So we'll split that up. And when you split this up, remember that since this is like a polyatomic or whatever you call that, stays together, this little 2 means that this CO3 has a 2 charge. And since there's not a number, it's not in parentheses and has a little number out here, it means Na just has a 1 charge. So, Na will have a positive or negative charge. Well, it's an alkaline earth metal, so it's going to want to
Evil person.
lose an electron, right? Because it needs to go this way in the periodic table to get its perfect valence outer shell. So it's kind of a positive charge.
Good.
So
Well,
you don't write down the
See if it's-
little 2.
What's that?
The little 2. Na2. You don't write down the 2.
Na2?
Yeah.
No. That's just when it's in this formula right here. Because alkaline earth metals, wait, no. It's alkaline metals
I'm kind of confused.
exist as plus ions.
Were you supposed to balance it first? No, that.
It is.
Oh, it's unbalanced. How'd you balance it?
The NaCl on this side needs it too. That's the only thing. You probably could have kept those.
Okay. So far, if that makes sense. So this dissociated into a sodium ion and a carbonate ion. This is what a carbonate ion exists as. You can see that on the table. And this is what a sodium ion exists as. And calcium chloride is also a strong acid. So it will also dissociate into ions. So calcium, when it exists as an ion, it's in the second row of the periodic table, or the second group of the periodic table. It's not the periodic table, it's not the first row, it's the second one. So that means when it's by itself as an ion, it's going to have a 2 charge instead of just a 1 charge. If it was in the first group, it would just be 1 charge, and you just write it like that. But since it's in the second group, it's going to be a 2 charge. And then chlorine. Chlorine exists as an ion. It's all the way in group 17. Only needs 1 more electron, so it's just going to have 1 more negative charge. There's the yield. And then here we have a solid, where there's S beside this calcium carbonate, so it's insoluble because it's not aqueous, it's not dissolved in water, so we're not gonna split that up. And then NaCl, aqueous, okay, same thing.
That's not a final answer, is it?
No, it's
I
not.
didn't think so.
No, this is not the net ionic equation. The net ionic equation is your final answer. This is just our ionic equation, because now we split up into all of these ions. So now we look, are there any that did not change at all during this whole process? That were completely unaffected. Which ions did not change?
Ions or
Sodium did not change. And chlorine. Chlorine did not change. It didn't gain any charges, or it didn't combine with anything. You see here the calcium went from a calcium ion to calcium carbonate. The carbonate went from just plain carbonate to calcium carbonate. So those two got changed, but the Na didn't change, chlorine didn't change, and so we're going to erase those from the equation, and now that's going to give us our net ionic equation, which will be CO.
Do you need to write the charges?
Yes. Yes. You need the charges. If that makes sense.
Does nothing happen with the 2?
Here?
Yeah. Nothing happened with that? Doesn't change anything?
No. Let me check. this would have been left in, like if the NaNC would have been left in the final equation, you have to make sure it was balanced then. But here it's balanced because the CO3 is the same and then the CA is the same. There's only one of each, so that's balanced. So this is our net ionic equation. So that's your answer from the first one. Does that make sense? Okay, now you want to know how to do this. So just make sure if it's aqueous, it means it's soluble because it can dissolve in the water. If it's not aqueous, if it's just a solid, it's not soluble. So you don't split those up. And then it's a strong acid or a strong base. Then split up. It's weak acid or weak base. And do not. Let's do the second one, which is F. KOH. That's hydroxide. It's water. Really close. So this one is smaller. I didn't put the little signs of it. And do you have answers for this? Yes. Yes, Bob? Yeah. Maybe?
I changed like both my answers.
Oh, okay.
Actually, no, I didn't change my last answer. I changed this answer.
Okay, so Izzy, what do you have for this one?
Like my answer, I have H positive plus OH negative yields H2O.
What you have, Parker? What do you have?
So, question first. Are we supposed to write, like when you're rewriting it, do you write well, I have the HF plus the OH negative yields H2O.
Okay.
Does
Here
the
it is.
HF,
What do you have? Everybody has. Okay, so let's look.
Did you turn it?
I had it.
Oh, okay.
Okay, so
That's what that is.
did you know that thing picks up on like all the noise and it's very hard to hear when there's a lot of extra noise? One of
So,
you,
like-
one of you yesterday was making a scraping noise for a
That's
while.
probably
I see.
okay,
Possibly me.
so HF. If we look on table 15.5, HF is right in the middle. So it's not a super strong acid. And let's look at KOH. OH, is a very strong base. So we're going to split KOH out. And you're only gonna split the acids up if they're in the strong acids category up here.
I thought you said if they're all soluble or all aqueous.
Well, that's why it says soluble first. It says soluble ionic compounds, but then it says strong acids and strong bases. So, yeah. So you'll only split acids up if it's in this top brighter blue part, strong acids, and you only split up bases when it's in strong bases. It is so hot in here. Oh my goodness. So hydroxide is in that strong base category. HF is not in the strong acid category. So we're not going to split up HF, but we are going to split COH. So let's do that. So this will stay the same. And it is. Is it balanced? I think, yeah, yes. It's balanced. So this is potassium again. This is in the first, and when you'll do these, and it says that have the net ion equation, the only answer that counts is your final answer. So if you get some of the stuff, like some of the ions in between wrong, that won't matter as much as long as you have your net final equation right. if you have something wrong in the substitute for that, I won't count that wrong. But potassium, first row, first group of the periodic table. So it's just gonna link this. OH negative. This is hydroxide. So those are the ions. Water is a liquid that doesn't split up. And then KF. This KF one here. I don't know if it's an acid, but
Does that make it? It said if it's either acid or base, if it's too weak, it won't be on this table. I guess.
which this is an aqueous. It's an aqueous substance. I don't think it's because if it was an acid, it would have hydrogen in front of it. That's not. But it does have a fluoride ion in it, which is just this. So, at the end of the day, this calcium doesn't change, or not calcium, potassium. This potassium doesn't change, so we'll erase those out. And so what we'll have left is HF plus hydroxide ion plus this right here. HF plus hydroxide ion plus H12 plus
Good ones are amazing, but What? They did.
Okay. I'll leave the last one. You guys can work on that, and then you can score it. You can score key. See if you get it. See if you can get that one. Can't, then we'll work on it more either tomorrow or something like that. Just make sure. So we have to keep it moving.
Or something.
What was that?
It's steaming here. How are you alive?
I know, right? It's not gonna be.
Different girls in here. I'll tell you what. I'm exhausted.
Do you think Maggie could hear anything? I don't think Maggie needs it anyways. She's such a Hermione Granger.
Wait, yeah.
Alright, so let's go to over to page 261. 261, concept review questions. So, number one, this is on page 61, concept review number one. How do the relative concentrations of hydronium and hydroxide compare to pure water? Izzy.
There are approximately one hydronium and one hydroxide for every 550 million H2O molecules, or 1.00 times 10.
So,
For each one.
they are,
What?
if they're both one, they are,
I don't know.
are they different? Or, like, how do they compare in the concentration? Are they different concentrations or are they the same?
Same.
They're the same. So they're equal. That's what I was wondering.
So they're equal.
They're equal.
So we have equal and then different.
They are equal. That's what I have. But that's right too. There's one of each for every 500 million water molecules. But when they compare, they're equal. That makes it's a big point. What is a pH scale? Logan?
A scale ranging from 1 to 14 used to measure how acidic or basic a substance is.
Yes.
I don't know, I kind of made up an answer.
What was that?
I kind of made up an answer.
It was what they talked about in the reading. That's what they wanted.
Yeah.
So it's a little bit from what they gave. Do you have something else, Reagan?
I have a convenient way to represent the H3O concentration.
Yes. Should be something. It's like that question on that pop quiz. The negative logarithm of the concentration of hydronium ions is the pH scale. That's what it is. So pH scale, you could say it's a measure of the concentration of H3O plus ions. Solution. But you're right, the pH scale is a scale of 1 to 14 that says how basic, acidic, whatever it is. That's what we know the pH scale is. They're explaining what the pH scale actually is. Here, what it chemically is, why it was created, and what it actually means. When something is 7, when a pH of 7, what that actually means. Number 3, at what pH is a substance considered neutral? 4, how are the pH and pOH scales related? Is he?
If you add them together, then it comes to 14.
Yes, that's right. At 25 degrees Celsius.
Both express acidity and basicity.
Yeah. Yeah, that's good. So that's how they're related. At 25 degrees Celsius, if you add the pH and pOH together, they'll always come up to 14. The magic number.
That is 14.
What was that?
That is 14.
We'll see. Alright. So, that's all the questions we did. There. Okay, so let's go to, I'll go to the sections. We'll start talking about them a little bit. 15.4, equivalence and normality. Okay, so equivalence and that kind of stuff, don't get worried about this. I don't want it to be super confusing. So we talked about molarity before, which includes moles. Molarity, if you remember, is moles over liters. So that's molarity. And that's concentration. It's another way for concentration, another word for concentration. And concentration, like how much stuff is in a liquid. Concentration. So if I put 5 grams of sugar into a glass of water, concentration is 5 grams of sugar in the water. So molarity is moles over liters. So when we're talking about acids and how much concentration of acid is in this certain is in water, and then how much base we need to neutralize it. So maybe if there's acid rain coming down and it's making the rivers and lakes more acidic, which is a problem because it kills fish and other living organisms, either whether the river already makes something that neutralizes the acid or we need to add something that will neutralize the acid that enters it. So it's important to know these things, and instead of using molarity specifically or moles to measure how this is, they use equivalents. And equivalents are related to molarity. Equivalence just means how much, instead of saying the concentration of this and the concentration of this, they're just saying how much an equivalent is. It's a, what do you call it? It's not a constant, but it's a unit for when you have an equivalent, when you have one equivalent of hydrochloric acid or one equivalent of anything else. It means it means that it has the amount to supply 1 mole of protons. So, protons, as acid donates protons. So when you want something that has a pH of 6 or pH of 5, and you want to get an acid like hydrochloric acid to make it go down, to make water that's 7 go down to 5, well, if you know how many protons you need to make it do that, then you can find equivalence you need. Equivalent is just, it's a number, it's the same for 1 mole of protons. So, how much you need for 1 mole of protons. And it's related to, and you can tell what an equivalent is just by how many hydrogens it can donate. And remember, with acids, they always put the hydrogens at the front that they can donate. So, hydrochloric acid has 1 proton to donate, so it has an equivalent of 1. And sulfuric acid has 2 hydrogens to donate, so it has an equivalent of 2. So it's not too terribly hard, or it's not too. It's more complicated than that, but for right now, that's good enough, and it's good. And then the equivalent mass is just you take the molar mass of all this. So take molar mass, calculate all the AMUs, put them together, and then you divide it by 2, and that gives you equivalent mass, which is so if the molar mass of sulfuric acid is 90.00. So if it's 90.00 divided by 3, and you get 63. Equal equivalent. I don't know if I'm doing math right, but I think so.
Divided by 2.
What's that?
Is it divided by 2 or 2?
Oh, whoops. Yeah, I don't know why I did. I was just trying. So something that has 3.
I really wasn't remember that.
Yeah, Wendell was writing on it earlier.
Oh,
It's like naughty naughty. So,
I think it's hard not to fall in.
so
Let's see what really fast.
this acid can donate 3 protons of hydrogen. So it's equivalent to 3. So you just divide it. And then a molar mass of 90.00 divided by 3 gives you the equivalent mass. And you want the equivalent mass because if you know that, you can say, well, you know that 30 grams of sulfuric acid will supply enough to make the pH 2. Whatever that 3 protons of hydronium will suffice. So there's another term for this now, or there's another term for the equivalence and molarity, because you can connect those two, which is normality. So normality is concentration of a solution expressed as the number of equivalents. So the number of equivalents that we were talking about earlier, if it can donate 3 protons of hydrogen, that's equivalent of 3. So molarity is moles over liters. Normality is just like it, except it is equivalence over liters.
so more normal.
What was that?
So more normal.
Yes, it's a little bit more normal. So you see the only difference is that molarity has moles over liters, normality has equivalent over liters. That's the only difference. So they are related because they both have liters. So they are related. So there's some questions like this down at the bottom, but normality. So something like HCl is only we can say M equals M for molarity, N for normality. So they both equal 1 because normality. So it only has one hydrogen that it can donate. So it's equivalent of 1. And then so the equivalent molarity is 1. If it has, I should put the N first. Because if we have something like I said, sulfuric acid before, then this now has, so for every, since it has 2, it equals the equivalent of 2. For every molarity, now equals 2 molarities. So if you say something has, if this would have a concentration of 18 molarity, all you have to do is just equivalent, 1 equivalent equals 2 moles of hydrogen. So we can just times 18 by 2, which is 36. So now you have your molarity. The normality. Molarity for normality. So very confusing. You can read that section again. Here, and there's some application questions on here. But let's go to ionization of water. So this is important. This is the reason why the pH scale is the pH scale. What it actually means, what it does. So anytime the water that's in Izzy's cup, water that's in your water bottle, at very low times, just a fraction of those water molecules are turning into hydronium, and a fraction of those are turning into hydroxide ions. But at the same time, they're zipping back into water molecules. So, just, you could say, water is making positive and negative. This is a very small number, very small amount. So, when we talk about this, we talk about water making, so water, one of these waters donating a proton or hydrogen, donates a hydrogen, according to Bronson and Lowry, that's an acid. If it donates one, it makes hydronium, also loses one, it makes hydroxide. Because there are water molecules that are all bumping into each other. So there's a chance that this can happen. But then they also go back into water molecules. Yes. This is why water can be both an acid and a base. Because it can make hydronium ions and it can also make hydroxide ions. But since they can go back, we can call this an equilibrium. Because they can make them and they go back to water. So it can have an equilibrium constant, which is called the ion product constant of water, which is Kw. And since water is a pure liquid, we don't involve it here. So we just have these two, which is the concentration or the molarity of hydronium times the molarity of hydroxide. Now what is this? So what are these two be? And what is Kw? And scientists know this really well because it's an important number. Because Kw, pure water, so the ion product constant of pure water at 25 degrees Celsius is always always 1.00 times 10 to the negative 14. That is the product, ion product constant of water. So pure water at 29 degrees Celsius has equilibrium constant. That's its ion product pure constant. What does that mean? What does that mean each of these are? Well, you just have to square the, or not square it, but a little thing. I can't think of the little
Square root.
square root. Yeah, we just find the square root of this, which would just be 10. And this one would also be that. Well, what does this mean? Well, so what we said, the negative logarithm of the concentration of hydronium is the pH. What does negative logarithm mean? That's just a negative log, like a log of a tree or something like that. This is the pH right here. This is how you find pH, negative log. Does anyone know what negative log means? Have you ever used it on your calculator? What was that?
I did earlier. I used my calculator.
So, log is really easy. Logarithm. It's the base of 10. Just means it takes the power of 10 away. So, right here, takes the 10 away. So all we have left is 14. And it only does stuff to the right of the decimal point, so it takes this away too. Negative 14. And then if we have negative logarithm, negative, negative cancels this negative out, so all we have left is 14. That's all. So, here, if the concentration of hydronium is 1.00 times 10 to the negative 7 power, we slap that in there, and we slap a negative logarithm on it. All we have left takes the logarithm, takes away the 10, and everything else beside it. And since it's negative, takes the negative away, all we have left is 7. So, and since this is the pH, that means the pH is 7, which is neutral, which water is neutral at 7. So, that's why the pH scale is from 1 to 14, and that's why 7 on the pH scale is neutral. Because water is neutral, so anything that has this anywhere close to this number, 10 to the negative 7th power, is neutral, or from 6 to 8, anywhere in between there. So, this is why this is important. So, when you add an acid, acids donate hydrogen ions, or they donate protons, which make these. So if you add something, if you don't know if it's acid or base, if you add something and it increases the concentration of this, it's going to make it more acidic, go down. Because again, if you have something that's, so maybe this is not water, maybe this is like hydrochloric acid, and it's 1.00 times 10 to the negative 4th power. So if you put this down here again, slap the logarithm on, it's going to take all this away, logarithm's going to take this away, and then the negative's going to take the negative away, so we got 4. pH is 4, which means it's pretty acidic. So if that's hydrochloric acid, so it's not that bad, it's not that hard. So if we find the pH is, example 15.5, find the pH is a couple of these. So the first one, number A, so the hydronium concentration is 6.25 times 10 to the negative 8th power. So is that going to be an acid or base? Or is it going to be neutral? So actually, if you put this in your calculator, do it. It's basically neutral. Well, if you would put your calculator, because again, this is 1.00, so it's not going to affect this number here. But if it's a number like 6.25, logarithms only count numbers to the right of the decimal point. But this does have some numbers after the decimal point, so it will change this number a little bit, or the logarithm, like the final answer. Let's see, we'll have to do that on your calculator if it has a logarithm thing on it. Hopefully it does. So, if you just punch this number in and then hit log, it'll give you your number. And since it's negative, it'll cancel this negative out. That's really long. That means since it is negative, it starts with negative, it's a little whack. So when you increase the concentration of hydronium ions, it decreases the pH scale. Increase the hydronium ions, but decrease the pH. So numbers that have a really low pH have a really high concentration of hydronium ions. And the opposite too. And POH is just, POH is for hydroxide. That's why it's OH. This is hydroxide. That's for hydroxide. So you can do the same thing with, so we said earlier, logarithm, or the pH is logarithm hydronium. But if you want to do it with hydroxide, you can do that as well. That's just the POH. So you can do that too. That's just the POH, not pH. It's POH. And if you figure that out, then you can figure out what the pH is, because you know that if you add the pH and the POH together, it's going to equal 14. So if you add the POH, then it's 8. And so 1 plus 8 equals 14, 6. So that means the pH must be 6. So it's probably pH is something acidic. So that's all for that. They talk about indicators too, which you guys know about indicators. Litmus paper, if you stick litmus paper in acid, it'll turn red. Blue, base will turn blue. They have little things here too. Blue is basic, so if it turns to blue, it means it's basic because they both start with B. And then red is acidic because they both have D's in them. So hope you remember that. But that's just a basic acid base indicator. If you want to do a more convenient, more precise, use a pH meter, which is electronic something. Electronic like a food thermometer thing. They said it's for pH. And then they also talk about universal indicators and pH paper, which is just like what you use for your swimming pool. It's not just one piece of red paper, you stick it in and it turns blue. Oh my goodness. But it has levels on it. And then it has a thing you can measure it with to see it can measure a bunch of different pHs. It's not just red or blue, but it can measure a bunch of different pHs to indicate what it is. Okay, that's all for that. Your homework tomorrow is reading pages 261 to 263. 61 to 263, and answer on page 261, application 1 through 3. And on 263, answer concept view number 1.